In this video, we're going to describe and discuss enumerators. An enumerator is a little bit like a Turing machine, except it produces a sequence of strings. So it generates or enumerates a language. An enumerator is a bit like a Turing machine. It's got a tape that's infinite, and it's got a finite state control that looks a lot like a Turing machine's control. But it also has something called a printer. So it can produce strings. The operation is pretty straightforward. Initially the tape is empty. Okay, there's no input to an enumerator. But instead what happens is it produces a series of strings and prints them on its printer. So we say that this machine enumerates, or it lists out, or it prints the strings that are in a language. So it defines a language in a similar way to a Turing machine, but it's a little bit different because the Turing machine either accepts or rejects strings that are in or not in the language, whereas the enumerator simply prints out all the strings that are in the language. An enumerator might halt or it might loop. Okay? Those are its two possibilities. It either halts or it loops. And in general, a language is infinite. Most interesting languages are infinite, and so the enumerator will run on forever. In fact, all finite languages are regular, so all interesting languages, I guess we can say, are infinite. The enumerator is allowed to print out duplicates, and the language is still the set of strings it prints out. So we just ignore the duplicates. And we allow our enumerator to print the strings in any order. So it doesn't really matter what order they print them in. Just a question of whether it prints a string or not. So here's our basic result. A language is Turing recognizable if and only if some enumerator enumerates it. So they have the same power as Turing machines. And our proof is, like we've seen before, it's a proof of construction. Given an enumerator, we're going to construct a Turing machine. Given a Turing machine, we're going to show how to construct an enumerator. So we're going to go in both directions of the if and only if. So let's look at these two parts in a little bit more detail. Given an enumerator, we want to show how to construct a Turing machine, M. So how's it going to work? This Turing machine should accept inputs, and we've got an enumerator, and basically what we're going to do is run the enumerator as a subroutine in the Turing machine that we construct. Okay, so for a given input W, to test whether it's in the language or not, if all you've got is an enumerator, then what the Turing machine is going to do is it's going to run the enumerator, and for every string that the enumerator produces, it's going to compare it to the input string W. And if we find a match, then our Turing machine will accept. So, to say it again, given an enumerator, we can construct a Turing machine that works the same way. The Turing machine has as an input some string, and it tests it to see whether it's in the language or not. And so, the way it works is it runs the enumerator as a subroutine, if you will. Every time the enumerator prints a string, the Turing machine that uses that enumerator will basically compare it to the input string and see if it's a match, and if so, it will accept. In the other direction, given a Turing machine, we want to be able to show how to construct an enumerator. So enumerators in Turing machines are very simple, and just as we can use a Turing machine as a subroutine, we can use a Turing machine as a subroutine in the enumerator that we're building. So let's assume we've got a Turing machine that can accept or that can recognize a given language. So how can we construct an enumerator that will list all the elements of that language using that Turing machine as a subroutine? Well, the idea is to run the Turing machine on all possible strings. Okay? We assume we've got some alphabet, so we can enumerate all the possible strings. We can list out all the possible strings. And so we run m on all possible strings, and if m, the Turing machine, ever accepts on a string, then the enumerator that we're trying to build should print it out. But of course the problem is that m is just assumed to recognize elements of the language. So the Turing machine might loop on some particular string, yet we want to try other strings as well. We want to try all possible strings. So we have to have a way to run all these simulations in parallel to find any string. If our Turing machine that we're given would accept any string, we want eventually to have the enumerator that we're building printed out. So let's look at this last part a little bit more carefully. What we want to do is run our Turing machine on all strings simultaneously. In other words, we want to have some sort of way to do parallel computation. What we can do is we can list out all the strings, all possible strings. Let's say our alphabet is zeros and ones. Well, in sigma star we have lots and lots of strings, each getting progressively longer. Unfortunately, the computation on any string in this list might be infinite, and we want to make sure that we don't get stuck looking at one string trying to determine whether it's in the language or not. We want to try all strings, and if our Turing machine would accept on any of them, including ones way, way, way out there, the millionth string, we want to be sure to print that out. And so we might have situations where our Turing machine might loop on the fourth string, let's see, 1, 2, 3, on 0, 0, but the seventh string, 5, 6, 7, might actually be in the language, and our Turing machine might accept that. So somehow we have to figure out a way to interleave all of the Turing machine computations. So in the enumerator that we're building, we can run this Turing machine on all strings in parallel. We work on the first string a little bit, then we work on the second string a little bit, and so on. And eventually we're going to go back to these strings and do a little bit more work. But we've got to schedule things in such a way that if there is any string anywhere that is accepted, we can do an arbitrary amount of work on that string, and so find out that the Turing machine accepts it, and then print it out. Okay, so here's an algorithm that will do what we want. We want to try every string, S sub j, and we want to try it for an arbitrary number of steps. Okay, so I is going to be the number of steps we execute, and j is going to be the string. So let's see what we have here. We have two loops, two nested for loops. The outer one is an infinite loop, so we're going to do I, 1, 2, 3, all the way up to infinity. And for each I, we're going to let j run from 1 up to that I. Okay, so with this sort of nested loop, you should be able to see that every pair of numbers will eventually be encountered. Okay, eventually I will reach some high number, higher than whatever j is, and eventually we'll have that pair generated with this nested loop structure. So what we're going to do inside this doubly nested loop is simulate that Turing machine. And we're going to use the jth string in our list of all possible strings as the input. And we're going to run the simulation for I steps. And if our machine accepts that string within I steps, then we know it's part of the language, so we print S sub j. So regardless of what string you have and how many steps it takes to accept it, eventually we will have I and j such that the machine will be simulated on that string for I steps, and we'll discover that that string is accepted by the Turing machine, and we'll print it out. I have an example here coming up of how this thing works. So let's assume we've got a Turing machine, and it accepts some strings and not others. And in particular, let's assume that it accepts S1 after 3 steps of execution, not very much. And it accepts S3 after 4 steps. And maybe it infinite loops on S2. Maybe it never accepts on S2. And maybe it rejects others after a certain amount of time, but we're only concerned about the accepts. So this is showing the doubly nested loop pattern. Here's I. I is the number of steps we execute. Okay? For I, we just check, for 1, we just check S1. For 2, we let J run from 1 to 2, and we check S1 for 2 executions, and S2 for 2 executions. And then when I is 3, we check S1 for 3 steps of the computation. We check S2 for 3 steps of the computation, and we check S3 for 3 steps of the computation. At that stage, when I is 3 and we're checking S1, we find that S1 is accepted after 3 steps. So we print out S1. And S2 never accepts. It's a looper, remember. S3 doesn't accept yet after 3 steps of execution. So then we increase I to 4, and we try strings 1, 2, 3, and 4 in order. We do 4 steps of the execution of the Turing machine on string 1. It accepts again after 3 steps. So we print it out again after only 3 steps. We try S2, nothing, because it's going to loop forever. We only do it for 4 steps, though. And then we try string 3 for 4 steps, and after 4 steps, it accepts. And it will accept forevermore. When we try to execute that same string for 6 or 10 steps, it will always accept after the 4th step. So we'll find out that it's accepting. So we print things out. We print out S1, and we print out S1 again, and then S3, and then we print out S1 again, and S3, and we keep going. And so you can see that we definitely are printing out some strings more than once. We print out duplicates. But this is still a perfectly valid enumerator. So you can see that given a Turing machine that recognizes a language, we can produce an enumerator that recognizes the same language. So the proof has both ways. Enumerators and Turing machines can both be used to define the class of Turing recognizable languages.